Okay, today we're going to look at a thing called a hypothesis test. A hypothesis test is something you do whenever you want to test a claim like, hey, this vaccine really works, whatever. You want to formally test a claim. What you do is you set up what's called a hypothesis test. And that's what we're going to look at today, and we'll also see this again in our Excel lab that's coming up. So, let's see. First, it's good to be kind of aware of what kinds of claims can be proved or not, except wait, I should not have said that because hopefully you remember this came up earlier. So I'm going to say remember always, just in case you're not remembering now. Statistics never proves anything. That's an S. Statistics never capitals. Proves capitals. Anything capitals. Never use the word prove or this proves this in writing your conclusions to your hypothesis tests. Statistics never proves anything. That's worth an exclamation point. That's worth putting in a box. You can't prove anything because it's all just chance. It's all just probabilities and stuff. It's all based on probabilities. Maybe I'll even put that down here. It's all based on probabilities. And reject or support. Those are the only two options. The only two conclusions we can actually draw. We can reject a claim. We can support a claim. We can't prove anything. But rejecting or supporting are pretty much the only options. I'll just say the basic options. You might phrase things a little differently, but you might use the word reject, you might use the word support. You're never going to say prove. Never, ever, ever say prove. So, okay, so with that out of the way, notice I'm saying examples of supportable claims, because you can't prove anything. Claims that you could support, that you could find support and say, hey, I'm supporting this claim. Things like this. The effectiveness of this pill is more than 80%. Fewer than 10% of all wombats have green ears. Okay, the average body temperature is not 98.6 degrees. Do you notice anything about all of these? Notice these are all inequalities. Inequalities. This is a more than. This is a less than. This is a is not or not equal, right? They're all inequalities. Inequalities can be supported. That's the only kind of claim you can support. This supports that it's more than this. This supports that it's less than this. This supports that it's not that. Here's another claim that you could test, I suppose, but you won't be able to find support. You can't actually support an equals. This is an equality. So I'll write that there. Equalities, the temperature is, body temperature is 98.6. You can't actually support that. Equalities can only be rejected, never supported. So you might reject that claim, but you're not going to be able to support it. Can only be rejected, never supported. Okay, so this is the first stuff you have to kind of get used to up here. When you're testing claims, right, look at the kinds of claims you might test. The effectiveness is more than this, fewer than this, is not this, is this. These are the kinds of claims we can test. They're all kind of math claims, right? And keep in mind, you're never going to prove a claim, but you could support a claim. You could support a greater than claim. You can support a less than claim. You can support a doesn't equal claim. You're never going to support an is claim. So these are important things to keep in mind. So we'll get a little practice with that today. So before we do any actual math, I would just want to look at how we structure our hypotheses, and I'll explain what that is in a minute, and how we would write our conclusions. Okay, so there's two kinds of hypotheses that are involved in every test. And your first step in every test is going to be to write these two hypotheses. You're going to write what's called a null hypothesis and an alternative hypothesis. They come in pairs. So the null This is H sub 0, and a lot of people think of 0 as null. So this is like H sub null or H null, or it's the null hypothesis. This is always the equals part of the statement. And the alternative is always a less than, greater than, doesn't equal. It's not an equality, okay? So how does this go? Let's look at an actual claim. Soapy, the snake oil salesman, claims that his concoction is more than 80% effective at growing new hair. So I underline this part. That's where you're focusing when you're writing your hypotheses. The hypotheses, by the way, we're going to write them very, very short. We're going to say something like this. Okay. The null hypothesis. Now, what did this say? This says the null hypothesis is always inequality. Not inequality, an equality. So the borderline that we're interested in here is this 80% number, right? And we're talking about a proportion, right? 80% of the people, that's a percentage, or a proportion is another way to say it. So what we're interested then is P equal to the proportion or the percentage equaling, I guess 0.8 is a decimal, not a percent, but you get the idea. So it's the proportion is 0.80. And the H1, what's his claim? His claim is more than. And so that will be the more than. So take a look at this pair for a second here. Always the H0 involves equals. And always the H1 involves either a less than or a greater than or a not equals. That's always how it works. And you use the numbers they're talking about. Notice the snake oil and the concoction and the hair are not really important to this part. So this part is what's the numbers we're dealing with here. We're dealing with more than 80% effective. So 80% is our equals. And we're trying to say more than, so we'll try to show that. We'll try to show that it's more than 80%. That would support his claim if we can show that it's more than 80%. So there's our hypotheses. Cool. Now, test results. Once you've got your hypotheses, you have to go out and like sample a bunch of snake oil and people and have them put them on their heads and wait a while and see how many people actually grow new hair, right? You're going to have to actually run an experiment, see how many people grow new hair. And your experiment, let's maybe write this over here with a pencil. Okay, so you might want to write this over here. Maybe in your experiment you get something like, 90%. Or maybe in your experiment you get something like 10%, right? You're going to have to measure and get a number to compare to that 80%. And probability comes in there. You say, well, what's the chance of getting something at least this extreme? You might remember we looked at p-value before, a few lessons back. We're going to look at p-value again later. But for now, let's not worry about the p-value. Let's just say the p-value was low enough that we're rejecting the H0. If the p-value is low, in fact, let's write this. If p-value low, we will reject H0. That's worth writing right there. So you have to do the experiment. You have to get a result, and you have to say, well, how weird is this result? Well, if it and you're assuming, I should say this too. When you do your test, you assume this is correct. In other words, you do your test based on it should be 80% correct. Then, if you get a low p-value, which means it's not very probable that that is correct, well, if it's not very probable that it is correct because the p-value is low, you're going to reject it. Okay, so I didn't really want to go into that all right now, but it's nice to have some idea what's going on behind the background. So anyway, let's just say those are our hypotheses, and we're rejecting the H0. If we're rejecting the H0, that means we're supporting the H1. Okay, the H1s can be supported. If you reject H0, you're also at the same time supporting H1. We don't usually write both at the same time. I like to write both at the same time, but that's not typically how it goes. So we'll just live with this. So when it says reject H0, it also means that you support H1. And that would be the stronger way to state the result here. You would say, the data supports the claim. Which claim? The H1. What's the H1 claim? That it's greater than 80%. And actually, I'm going to put an empty parentheses here, and we'll worry about that much later. So something's going to go in the parentheses, but not yet. So the data supports the claim that more than 80% of users or whatever grow new hair. And that, of course, is what SOAPy is hoping for, is that we'll do a test and we'll find out, hey, look, it really is more than 80%. On the other hand, you might get a high p-value, which says, well, on the assumption that it's 80%, this is not a surprising result, and you fail to reject the H0. And then that's really all you can say. The data fails to support the claim. It fails to support the H1. Fails to support the claim. And again, there's parentheses, something goes there, that more than 80% of users will grow new hair, or something like that. You have to write out these sentences, by the way. I know it's people really hate writing sentences these days because it's like, you mean a pencil? Yeah. So anyway, or you could type it out. Anyway, you should write full sentences is what I'm saying here. So, okay, so this is one possible thing. We did a test for, is it really more than 80%? Again, the equals is your H0, the greater than is your H1. If you get a low p-value, you're going to reject H0 and support the H1, and that's the strongest way to say it, is to say we support the claim, and then you write the H1, that more than 80% grow. But if you fail to reject H0 because you have a high p-value, you say, well, you could say we've failed to you don't want to even talk about that. Address the issue at hand, which is the snake oil doesn't seem to be that effective. So the data fails to support the claim that more than 80%. It's not, doesn't seem all that effective. Now, in neither case did we say prove, right? Neither case did we say prove. Okay, so that's one example. I got two more of these under section B here. So let's look at this one. Willie, the conservation officer. Willie, the wallaby conservation officer, claims that fewer than 10% of all wombats, he does wallabies and wombats, fewer than 10% of all wombats in the province have green ears. Okay, so notice there's the math part, fewer than 10%. So without even worrying about who's doing what with green ears or wombats or whatever, you have enough information just looking at that to write your two hypotheses. So the H0 is going to be, and again we're talking percentages here, so proportion P, and the H0 is always the equals, and our cutoff is 10%, and the H1, which is what we hope to support, a successful hypothesis test will reject the H0 and support the H1. Anyway, we want fewer than. We're hoping to decide in favor of fewer than. So let's say we get a low p-value. We do the test, of course, and we go get a bunch of wombats and we see what percentage of them have green ears and so on. And maybe we get, based on this assumption, under the assumption that it's 10%, maybe you only get 1% in your sample. Well, that would be a low p-value, because if it's 10%, you would expect something like 10% of your sample to have green ears. So if it's only like 1% in your sample has green ears, well, you're going to reject the H0. You're going to say, I don't think so, it's a low p-value. Reject the H0, which again means the same thing as, or at the same time, means support the H1. And that's the strongest way to say it, is support the H1. The data supports the claim. And something goes in parentheses, we'll worry about that later. The data supports the claim that less than, or that fewer than, or whatever you want to say, fewer than 10% of all wombats in the province have green ears. Notice how you have to write out the whole sentence. I was mentioning that earlier. You really got to write out the whole sentence. Don't just put down something cryptic or symbolic or something. You want to have a sentence, an English sentence. So the data supports the claim that fewer than 10% of all wombats, that's their H1, it supports the H1, have green ears. Now if we get a high p-value, and what does a high p-value mean? It means, look, if we're assuming that it's 10% and then we get maybe 10 or 11%, well, that's kind of what you would expect. It would happen with a high probability, so it would be a high p-value. And if it's a high with an H in it, if it's a high p-value, then that means our assumption seems to be okay. We're not going to reject H0. We're not going to reject it. So I could say fails to reject 10%, but usually you want to kind of address it in terms of what the H1 is. And so I'll say, let's see, the data fails to support the claim. Something in parentheses, that fewer than 10% of all wombats in the province have green ears. It ain't easy having green ears, that's what they say. Okay, so the purpose is to get used to this language. Data supports the claim, this claim. The data fails to support the claim, this claim. Now the next example is a little bit different, so it's really worth looking at, but it involves the equals not equals. So nurse 3, example 3, Nurse Nellie claims that the well-accepted theory, if you will, that the average human body temperature is 98.6. She's been measuring temperatures all her life, and she says, no, that ain't right. That ain't right. So it's something else. Okay, so 98.6 is wrong. Okay, there's no less than, there's no equal than. Excuse me, there's no less than, there's no greater than. Therefore, it's a not equal situation that we're looking at here. So the H0 is always the equal, though. So the temperature, I'm going to say it this way, the mean temperature is 98.6 degrees Fahrenheit. That would be the H0, and the H1 in this case, again, she's not saying it's lower, she's not saying it's higher. I don't know why she's not saying it's lower or higher. She just says it's different. So it's just different is one of these. It's just different. Okay. So we take a bunch of data, and if we assume that it really is 98.6, we can calculate a p-value. Hey, we got 90 degrees. Well, that would have a low p-value, right? Because if you're expecting that most people have a 98.6, and then you take a sample of 1,000 and it has an average of 90, you'd say, well, that's not what I was expecting at all. That has a low p-value. That is not likely a chance result. Something's going on here. I think this is wrong, is what you're saying. I think that's wrong because I got 90. That's not it. That's wrong. So reject H0, which again is the same thing as supporting H1. But it's a little awkward to say supports the claim that it's different. That's a little weird to say it that way. So let's say it this way instead. And this, I think you'll agree, is a little more natural. The data warrants rejection, something goes in parentheses, of a 98.6 mean body temperature. Doesn't that say it a little more strongly? Doesn't that seem strong? The data warrants rejection. No, it's not 98.6. That's better than saying it supports the claim that it's different. That doesn't, I don't know, it doesn't sound like it would win a debate. You want to win a debate? Rejection, rejected. It's not 98.6. The data warrants the rejection with magical parentheses of a 98.6. Okay, good. Well, what if you fail to reject H0? You don't want to say fail to support the hypothesis that it's different. Fail to support the claim that it's different. No. Now you can't say you prove that it's right. So actually I'm going to write down some notes here. Fail to reject H0 is kind of saying that we did get a temperature. Our sample did come out somewhere near 98.6. Okay, so nothing is ever proved. So I'll put over here, i.e. we got something really close to 98.6 in our sample. So if it's close to 98.6, we're saying, well, that's kind of what we were expecting, so we're not going to reject the H naught. It seems okay. But nothing is ever proved in statistics, so we're not going to say we proved it really is 98.6. We're not going to say that we support H naught. You can never say support H naught. Okay, you can only support an H1, not an H naught. So what are we going to say? Well, this is about the strongest thing we can say, so I'll go back to blue. The data is consistent. The data is consistent with the claim. I'm not going to say with the claim. That sounds goofy. The data is consistent, and again, magic parentheses, with a mean body temp of 98.6. That sounds good. And that's a 9. Okay. So I guess I don't use the word claim here or here. That's interesting. I use the word claim up here, right? The data supports the claim, fails to support the claim. The data supports the claim, fails to support the claim. But here I don't use the word claim. I say warrants rejection of a body temperature of this. Consistent with. Now consistent with, that's not the same thing as proof. It's not even the same thing as support. It just says, well, we weren't surprised. That's really all it says. We weren't really surprised, so it's consistent with it. No reason to think it's different. Nothing to see here. Okay, one more example for today. And now I get to tell you what goes in those parentheses. So when you're conducting tests, it involves not only these hypotheses, which are important to understand, that's why I wanted to do them separately, but it involves p-values and significance levels. Now these are things that we did kind of see briefly in a few lectures ago. I said, what's a p-value and what's a significance level? And so let's kind of bring back those definitions here. I'll just kind of line that off or something, right? So what's a p-value? Do you remember what a p-value is from a few lessons back? It's kind of like how likely is it to get such a weird result. So I'm going to say the probability, because it is a probability, that a result at least as extreme as this one, whatever one you're looking at least as extreme. It's the probability that you get a result at least as extreme as this one. Could be, it's not just a probability, it's the probability that it could be just a dumb luck thing. Could be just a dumb luck thing. What does the probability mean? It doesn't mean the probability of getting that particular result, but something at least as extreme as that result. And it's the probability that it could be just dumb luck. In other words, that it could have happened by chance. So, for example, you flip, you flip 4 coins and you get 4 heads in a row. Well, it's a 1/2 times 1/2 times 1/2 times 1/2 is 1/16, which as a decimal is 0.0625. So the probability of getting all 4 heads is 0.0625, and so that's you might say it's a p-value of 0.0625 of getting 4 heads in a row, because you can't really get any more extreme than that, I guess. But so usually it's at least as extreme. This result is weird. How weird? It's less than 1% chance that it's going to happen. Okay, that's weird. So, that's what the p-value is telling you. And then the significance level, there we go. Significance level is basically your cutoff at which you will reject your H naught. So the significance level is the p-value below which you will reject, or we will reject, our H naught. So remember we used to say you can use a criterion of like 0.05 significance level, 0.02, 0.01, or maybe 0.005, or maybe 0.002. These are typical, or you could get really carried away and use, something like that, whatever. You choose a significance level, and 0.05 is kind of our workhorse. 0.05 is for like common everyday use. So you choose a significance level like 0.05, and 0.05 would mean it's a 5% chance, or of the something happening here. So if your p-value is less than the alpha, by the way, we use alpha. P-value, we usually use just a p. If p is less than alpha, we reject h naught, is basically what happens here. Because it seems like our test has an unlikely result. If h naught were true. So let's look at this problem here. So let's get this stuff out of the way. Let's switch colors. What do we got here? Give me the green. Okay. Biff, the YouTube pollster, claims the majority of voters will vote for Proposition 88. That's his claim. He says he's been talking to lots of people, whatever. He did his own poll. I don't know. But that's his claim. But he's just a YouTube pollster, so you decide you'll test the claim yourself. How do you do that? You go and you do a nice, simple, random sample. Remember how important that is. Don't just go to the mall, but a simple random sample of 600 voters. And do we get a majority? Well, we got 320 in favor. That's more than 300, right? That seems like a majority. The question really is that a significant enough majority that we can say it's not just chance? It really is more than 50%. Because, you expect 50%, you expect 300, but you might get 302, you might get 298, and that would not be surprising at all. The question really is 320 surprising? Is that surprising, or is that not surprising? So you have to do math to find that out. But first, let's structure our test here. So I'll put it old. So what's majority? Majority is 50%, right? So that means that the equals 50% is our h naught. And the h1 would be, well, if it's a majority, you want more than 50%, right? So the h naught is always the equals. The h1 is always a less than, greater than, or not equals. In this case, greater than to show a majority, to show that it's more than 50%. What's going to happen here? Well, let's think in terms of this. It's a binomial distribution, right? Because it's, you got so many voters and there's a certain percent chance that they're in favor or whatever. So we expect, if we assume, for the sake of the test, for the sake of conducting the test, that this is true. Assume, for the sake of conducting the test, that this is true. Well, if that's true, and we take a sample of 600, we would expect 300. And we got 320, and I don't know how far out this is, because I don't know what the standard deviation is. But we'll just kind of, whatever. Now, the p-value of 320 would be the area to the right, because we're interested again in it being greater than 50%. So greater than 50% is to the right of our, that would be our test value. And we want to know, what's that area? What's the probability of getting something even bigger than 320? Is it a lot? If it's a real good chance, if it's a high p-value, that means, 320, that's within what we expected. If it's a low p-value, it's not what we in the range of what we expected. We'll reject the h naught. Well, how are we going to figure out the p-value? You come back up to what I was kind of not looking at. It's a binomial distribution, right? Whenever you have, you're going to do flip coins or roll dice or ask a bunch of people a certain yes-no question, right? Then it's a binomial distribution. Now, you have to go into Excel, so hopefully you'll be able to do this. I only have one problem on the homework where I actually require you to do this, so hopefully you'll find your way to Excel, and then you'll get into any cell in Excel, any cell that's in Excel, and in that cell you type this. Now, the equals is very important. You have to type the equals, because that's what tells Excel, hey, I want you to calculate something, please. And then when you type all this stuff in, what it's going to do is it's just going to put the answer in the cell. So this is the part that you type into the cell, and when you hit equals, this is what you'll see in your cell. And what that represents is the area left. Area left of what? Well, it says binomial distribution, and notice here's our 320 and our 600. We put those two numbers there, right? So that's like the how many did we get, and that's like the how many trials did we have, and that's the assumption right here, the H0 assumption that it's a 50-50 probability. That's what we're testing. We're testing that is it really 50% or is it greater than that? That's our cutoff, if you will. And the 1 is for cumulative area left. So when you get this number, what does it mean? It means cumulative area left. Okay, now I'm going to get a new color. So the cumulative area left, 0.95, let's just round that to 0.953. So Excel says that the area to the left of the 320 here is 0.953. So the area to the right, 1 minus 0.953, which is 0.047. That is our p-value, 0.047. Now, we didn't say what significance level to use, did we? Let's say that up here. Use alpha equals 0.05, i.e. a significance level of 0.05, because that's our general everyday workhorse value. When we're just doing common things that don't matter that much, we tend to use a 0.05 significance level. If it's less than a 5% chance that this would happen by chance, then we're going to reject that H0. That's what we're going to do. So 0.047, we're going to, using alpha equals 0.05, we have p-value less than alpha, and that means we reject the H0. So, writing it up here, reject H0. That means we've supported this. Support H1. The data supports the claim at the 0.05 level, because it doesn't support it at the 0.01 level, right? It only supports it at like a 0.05 level. But it supports the claim at the 0.05 level that a majority of voters are in favor, I guess, of Prop 88. So this is the part, let's try that. At the point, no, that's not what I wanted. Come on, you. That. At the 0.05 level. That's the new part. That's what goes into all these parentheses. Okay, so just, we can do that real quick, like, right? So let's just assume we always used a 0.05 level. At 0.05 level. That's actually a very important thing to put into these statements, and so that's why I'm putting them in now. I'm fixing my previous stuff. You should always say what significance level you're using, because if you're using a 0.05, they might not be as impressed as if you're using a 0.001, then they have to be impressed, right? That's impressive. Okay, I guess that's it. So this was, I actually showed you how you can actually calculate a p-value in the case of a proportion. Excel can also do it for the case of means. You want to get the p-value, you want to test a claim about a mean, the mean temperature is 98.6 or whatever. I don't want to do that here, that would add too much. So I'll just leave you with this one Excel command to kind of get used to in this assignment, and then when we do our Excel lab, I'll show you how to handle means and stuff. So this never goes in all at once, okay? Please don't be surprised, and it didn't go in at once for me. Please don't be disheartened or something if you need to come back and kind of, well, play it all through again. Play it all through again, and hopefully the second time through, you might pick up a little something that you were missing and say, oh, that's what I needed to remember. That's what I need. Now I get it. Now I get it. Okay. 2 reads is often a good idea for a book. We don't usually go to lectures twice. That's why we have notes. But looking at your notes is good. this is better. You can actually come back and play at double speed, or if you have to, or 1.5 speed or something. But be able to take a claim, structure null and alternative hypothesis, and figure out p-values. We'll do more of that later. But then, most importantly, given the p-value and given the significance of alpha, if p is less than alpha, you will reject the h0, support the h1. Be able to write these sentences. If you fail to reject h0, be able to write these sentences. Please write sentences. And then we got these two special too. Warrants rejection consistent with. All right, my computer turned off. Bummer.